to help out too. So we're pretty fortunate, and I hope that everybody in the class is doing well as well. Oh, one second. It looks like it's picked the wrong microphone here. Oh, no, it says the right microphone. Okay, good. Okay, so we will start. I'll keep the chat open over here. So a couple of things. So first, the multiple choice part of the exam will begin this weekend. I just want to show you where you'll be able to find it on my courses. Let me share my screen over here, and you can see what's going on. Right? So here, when I'm sharing my screen, if I went into my courses right here on the home page, there's two places you'll be able to find it. We'll want to access it through the quizzes because that's where we'll be able to answer the multiple choice. So right now you shouldn't be able to see this, but I do have it coming available on the 25th, which is Saturday at 9 a.m. and closing. Well, I guess the due date I put for midnight on the 26th, but I left it open and accessible until the 27th at 2 a.m. So you will be able to access this once it's available, once we're in that time frame, right? So you just be able to, just like when you do your quizzes, you come into quizzes and you pick this one, and it's linked right to your grade on the final. So I'll try to have that grade probably hidden, I think, so you don't see it right away, and then maybe when the exam is over, then you'll see what that grade will be. The other place, if for some reason this does not work, you can also, if you go in here under content, I made a new, I don't know what these are called, folders for the material for the final. And this is also where the long answer problems will be found. But you can click on here. You can't do it yet because, again, it's hidden from you and it doesn't open until the weekend. But when it's open, you can click on here and you'll see sort of a PDF version, the same kind of thing you would see on an exam. But in the best case scenario, you submit your exam through your quizzes, right? So you'll submit your multiple choice answers there. If for some reason that fails, though, we have a little bit of redundancy here. You can look at this handout and either print it out and circle your answers, or if you don't have a printer, you could probably take the PDF and sort of make note of them, or even just looking at the PDF and write down your answers and scan something or send me an email. That will work too. But I envision no problems with the quizzes because it's something that we've sort of consistently done throughout the course, but just in case there's this other mode as well. So does anybody have any questions about how to access the multiple choice part of the exam?
I have a question on how the multiple choice problem of the exam will go.
Okay, so the way that it'll work, do you mind muting your microphone so it doesn't echo through? So the way that it will work, the multiple choice will open on Saturday at 9 a.m. And that quiz will remain open until Sunday at 11:59 p.m. So it's open for 39 hours. And in those 39 hours, you can access it just like you would access a quiz. And all the multiple choice questions have been populated in the quiz in the same way that they're on the PDF sheet. So you'll go through and answer the questions like they were a quiz, and then you'll hit submit, and then and that will be the end of the multiple choice exam. Does that make sense, or does that answer your question?
Is there like a time limit to the amount of time we have to access the multiple choice?
So there's not a firm time limit. So we've put in a recommended time of 2 hours, which, again, if this was a multiple choice test in a room, we would assume that it would take approximately 1 hour to finish, but we have not implemented a time limit. But that's not to say that we expect people to sort of have it open all weekend. So we'll watch that time limit, but I think, there is no time limit, but we can see when you access it and when you and when you close it. But no, we're not enforcing any kind of a time limit on that multiple choice, except I guess the 39 hours that it's open. Does that make sense?
Yep, thank you.
You're welcome. Yeah, but again, I guess the reason that we're keeping it open that long is to provide people with flexibility, and not because we like. It's certainly not written in a way that we think it'll take you 39 hours to complete. I think it's kind of just a normal multiple choice exam that you would see. So, but we obviously lots of stuff's going on, so we hope that the way we're delivering it is accessible to people. Any other questions about sort of accessing the multiple choice, or any questions about how the multiple choice or even the long answer part of the exam is going to be administered? Okay, well, this is our last class together, so I just want to say thank you again. It's been different, right? But I do think it's been fun, and I appreciate everybody's patience as we're moving through this sort of virtual part of the delivery. I also appreciate that 15 people have submitted the course feedback. I think again this is important to us. We all hope that we're not. That we're delivering material in the classroom again in the fall, that we're not forced to do it virtually like this. But even if we do, it's nice to know your thoughts. So I appreciate people taking the time. I believe that this is open until reading day, I think, which is, it's on here, which is next Tuesday, the 28th. I will reserve our normal class time on reading time as office hours. So again, it will be a little bit more, just like I'm running my office hours now. Please let me know if you want to meet with me during that time. I won't have anything specific prepared, but if people do have questions, I'm available. Just let me know if you would like to meet me, because I probably won't just be sitting, alone in one of these Blue Jeans meetings for an hour and a half. But if I know people are going to come, then I'll make sure that I'm there. So please, if you're interested in meeting with me on reading day or on my office hours, which are Friday and Monday, please let me know and I will be here. So I guess what this calendar shows, right, that we have the multiple choice part of the exam this weekend, the 25th and the 26th. As we've discussed, you can access this through my courses. Then we also have the long answer part of the exam will be in the scheduled time on SIS, which is the 30th, from 4:15 to 6:15, and we will leave that submission window open, I think, till 7:15 is what we said in the email. If anything comes in later than that, it might have to come in through different channels. So hopefully everyone can get it submitted in that time. Today, we're going to review the third practice exam, which is the practice exam for the third module, the module we've been doing virtually. But before we get to that, does anyone have questions about sort of the time frame of what's going on?
For the free response, other classes have required us to both submit our answers through a quiz and our full solutions to a Dropbox. Is that the case for this class, or is it just the solutions to the Dropbox?
Yeah, we thought about that. We decided against sort of the extra burden. I think we tried to go with maybe what we think is the answer where it's less stressful for students. So hopefully that's what we picked. We were thinking that having to submit in two different ways would make it more stressful. So we elected to only submit through the Dropbox. Any other questions? Okay, we will begin the third practice exam. So again, I'd recommend going through these on your own, but sometimes it's helpful to look through it, right? So our first question on the multiple choice, which dimensionless number is best interpreted as the ratio between the momentum and thermal diffusivity of a fluid? So here, when we look at kind of the way that I usually think about this is in internal flow. When we're looking at the ratio of the entrance length, we use the Prandtl number, right? So the Prandtl number is telling us sort sort of the relative size of the thermal boundary layer versus the relative size of the kinematic or velocity boundary layer. So this first answer is the Prandtl number. The second question, which dimensionless number is best interpreted as the dimensionless temperature gradient in a fluid adjacent to the surface? Here, this is the Nusselt number. For me, this definition, I mean, it's certainly true when you look at it mathematically, right? And we talked about how the definition of the Nusselt number and the definition of the heat transfer coefficient both rely on this temperature gradient, right? This dt by dx term. So it's really tough to know this in real life, right? So I sometimes think about the Nusselt number as a dimensionless convection coefficient, but that convection coefficient is proportional to the temperature gradient in the fluid right at the surface. So here the answer is C, the Nusselt number. 3, which dimensionless number is best interpreted as the ratio of actual heat transfer rate to the maximum possible heat transfer rate in a heat exchanger? So here, this is the effectiveness. So we have a similar definition for fin effectiveness, where it's actual heat transfer divided by maximum heat transfer. So if you have an actual divided by a maximum, when you're talking about heat transfer, that's an effectiveness number, right? So, here we're only asking these 3 questions, but you can see that there's this type of multiple choice question that's asking you for sort of a physical interpretation of the different dimensionless parameters that we're using. So if you're thinking about studying, these kind of questions do come up on exams. Question 4. Consider the laminar parallel flow over the entire surface of a flat isothermal plate as shown below. So in this picture here, right? What point along the plate experiences the largest temperature gradient in the y direction at the surface, and also the largest local convection coefficient? So here we have to remember maybe a figure like this, right? So this shows us the heat transfer coefficient and the boundary layer thickness as we move down the plate. So in laminar flow, we can see H, right, which is this problem is talking about, right? This, which is, like we said, proportional to the temperature gradient at the surface. So here, it decreases in the laminar region as we move down the plate, right? And then it's you get this unit step up when you go to turbulence, right? So that's this dashed line, because turbulence is kind of a transition. It's not just one length that happens. And then we have sort of the peak heat transfer coefficient, and then again it starts to fall with X. So this problem talks about a laminar parallel flow. So it's laminar the whole time. So we're only interested in the first part of this graph where we have XC. So we're going from X equals 0 to X equal XC. So here, the maximum heat transfer coefficient occurs right at the edge of the plate. So right at that leading edge of the plate, we have the highest heat transfer coefficient, and then it decreases along the plate. So here the answer is X1. Question 5, which of the following temperature profiles best describes the temperature profile in a heat exchanger where the heat capacity rate of the hot fluid is much larger than the heat capacity rate of the cold fluid? So here we have to think a little bit about what heat capacity rate is, right? So this is the big C that we've been talking about. So this is m dot times Cp. And we know that for big C min, we get a bigger temperature change. So if big C, here this is saying the heat capacity rate on the hot fluid is much larger. So if the hot fluid had sort of an infinitely large big C, and the cold side had a relatively small big C, what that means is that the temperature in the cold side would change a lot, and the temperature on the hot side would stay the same. So here, the answer is A, where we see the hot temperature. It's not labeled as the hot temperature, but it's the higher temperature, and the cold temperature is moving. Question 6. Consider a situation where a tube is transferring heat to a fluid as it enters the tube, transitions to fully developed hydrodynamic and thermal flow as it flows through the tube, and exits the tube. In what region of the tube is the convection coefficient constant? So here we know that in the entrance region, H is changing. But once we get to be fully developed, H stays the same. So this is true of the friction factor for a pipe. So the friction factor decreases until you get to the entrance length, and then it stays constant. And it's also true of the heat transfer coefficient, where it decreases at the entrance of the pipe and then gets to some steady state when you're fully developed. So here the answer is the fully developed region. Question 7. Consider water at 300 degrees Kelvin with some properties flowing into and through a 5 centimeter diameter heated pipe at a flow rate of 0.002 meters cubed per second. If the pipe is 100 meters long, at what approximate distance from the tube entrance does the flow become thermally developed? So in order to know about these development lengths, right, or the entrance lengths, the first thing we have to ask ourselves is, what's the Reynolds number? Because that'll tell us if the flow is laminar or turbulent, and the entrance length depends on whether we're laminar or turbulent. So we can use a Reynolds number calculation. So there's a couple different ways to get to Reynolds number, but in this case we have the dynamic viscosity and the density. So we can use the calculation on the right instead of the kinematic viscosity. So here we can put our numbers into our calculator, and I find that the Reynolds number is 60,000. Right? And here that means that it's turbulent because the transition to turbulence in an internal flow is 2300. So now we're turbulent, and the nice thing about turbulence is that the entrance lengths are easy to calculate, and they're the same hydrodynamically and thermally, and they happen 10 diameters into our pipe or a channel. So here that means that it's half a meter, which is one of the answers on my list. So I pick A. For part 8, what is the fully developed convection coefficient for air at 20 degrees Celsius with some properties flowing at a velocity of 4 meters per second through a rectangular channel that's 3 centimeters by 6 centimeters, which is at 40 degrees Celsius. And we're told a Nusselt number. So from the definition of Nusselt number, I can get an analytical expression for the heat transfer coefficient. So now I have an expression. I need K, which is given to me, but I got to pick the right K here because I know, oh no, there's only one fluid. So I pick K, and then I need the hydraulic diameter. So my hydraulic diameter is 4 times the area divided by the perimeter. So I know the dimensions of my channel. It's 3 centimeters by 6 centimeters. I put that in meters here. You could leave it as centimeters and then just convert at the end. You'd have centimeters squared, although they drop out. So I think it would be fine, right? But you get 0.04 meters or 4 centimeters. I put that back into my equation for the heat transfer coefficient, and I get just under 20, which is one of the answers on my multiple choice. So I pick C. If the correlation function for laminar flow over a plate with uniform heat flux is the expression given, what is the convection coefficient at 15 centimeters from the leading edge of the plate for a fluid with a bulk velocity of 1 meter per second and the following fluid properties? So here we have our Nusselt number correlation. I can rearrange this equation to get an expression for the heat transfer coefficient, because here I'm trying to find H, right? The thing that I don't know is my Reynolds number in this equation, so I have to use an expression for Reynolds number. I put data into my calculator, and I get that it's a very large Reynolds number, almost 175,000. Well, I guess it's not. I was thinking, when I said very large, I was thinking about flow through a channel, but this is over a plate, so that Reynolds number is actually not that big, right? So here we have a heat transfer coefficient, or an expression for the heat transfer coefficient, and we can put the Reynolds number value in. We're told the Prandtl number. We know K. X in this case is the distance from the leading edge that we're interested in. So it's 15 centimeters. Again, I have to get the units right here. I put all this into my calculator and I get a heat transfer coefficient of almost 1400. Again, this is an answer on my multiple choice, so I select E. For problem 10, we're designing a sophisticated titanium heat exchanger, shown in this picture here, that uses a proprietary gas to heat up water flowing at 2 grams per second from 27 degrees Celsius to 87 degrees Celsius. If the properties are known for the titanium, the water, and the gas, what is the rate of heat transfer to the water? So I know for either side, I can take m dot times Cp times delta T. So I look at this side and see, where do I know this information? And I know what the properties are for the water. I got to make sure that I pick the right properties for the right fluid here. So if I was just doing this quickly, I might write down the K value for the gas instead of the K value for the water, right? So I have to use the properties from the fluid that I'm interested in the temperature change of when I use this equation. And here I get 502. As I carry my units here, I get joules per second, but I know that joules per second are watts. So this is 502 watts. So that's the end of the multiple choice part of the exam. Does anyone have questions about the multiple choice? Excellent. We will move on to the first problem. Again, a Star Wars problem here. So Luke Skywalker is designing a geothermal cooling system for his above-ground home on Tatooine. To do this, hot air from outside his home at 29 degrees Celsius flows underground at a rate of 10 meters cubed per minute through a 15-meter long, thin-walled, 15-centimeter diameter circular pipe and enters his home above ground. The entire length of the pipe is situated underground, where the temperature of the sand and the soil is constant and uniform at 15 degrees Celsius. Assume the surface of the pipe to be at the temperature of the sand and soil. Ignore condensation effects inside the pipe. Assume air properties are given. So first, we're supposed to find what the average convection coefficient of the air flowing through the tube is. For part B, what is the temperature of the air leaving the 15-meter long underground section of tube? And part C, assuming the air entering the house is at the same temperature found in part B, what is the cooling rate in watts provided by the air entering the house if the house is maintained at 23 degrees Celsius? And there's a hint here telling us that air leaves the house at 23 degrees Celsius and at the same rate as it enters the house. Okay, so first, I always like to draw a diagram. So this is the diagram of our tube that runs under our pipe, right? So it's bringing air in, right? We know that it's taking it from outside where it's 29 degrees. We're told a flow rate, but it's a volumetric flow rate. I know that I'm going to want a mass flow rate, so I'm just going to go ahead and do that, right? So this 10 meters cubed per minute, I don't like dealing with this because it's in meters. It's a volumetric flow rate, but it's also per minute, and I want per second. So first, I change this to 0.17 meters cubed per second. I divided by 60. And then I had to get to kilograms, so I need the density of the air, and I think that's given in the problem here, right? So density here is 1.16 kilograms per meter cubed. So I take my 0.17 and I multiply by 1.16, and I get 0.2 kilograms per second. So now this looks pretty good. I know that I'm interested in flow through this pipe. So this is an internal convection problem. I have some information. The problem is nice because I know on my flow chart, one of the things I usually have to do is look up a bunch of numbers on a table. But they gave us a bunch of fluid properties, so I hope that's enough. And I'm given the geometry of the pipe, both the length and the diameter. I'm going to assume that the whole system is at steady state, that the material properties are constant, and the fluid properties here, I guess, that the pipe is isothermal. The problem tells me that I can assume that the pipe is at the same temperature as the soil for the whole length, that I can ignore condensation effects. So I don't know if anybody here's taken Thermo 2, but in Thermo 2, we talk about psychrometrics, where we sort of acknowledge the fact that air isn't just air, right? So there's water in the air. So as you cool it down, you get condensation, right? That's why you get dew on your window or your grass or maybe your car windshield, right? So we're going to ignore that any of that happens, right? We're going to neglect radiation and other losses. And we're going to neglect conduction resistance through the pipe wall. So we're going to what this means, right, is we're going to assume that the pipe has a thin wall and that the temperature on the wetted perimeter, right, so the temperature of the pipe that touches the fluid is the same temperature as the outside of the pipe, which we're assuming is the same as the soil. So now I'm going to run through my convection flow chart. Right? So first, we want to understand the geometry and the boundary conditions. So we know that this is internal flow because it's flow that's moving through this pipe that we're interested in. And we also know that it's got constant surface temperature. That's one of the assumptions that we've made. And we know that it's a round pipe, so I don't have to calculate a hydraulic diameter. So when we did these kind of problems, we said, okay, well, the things we have to think about are like, is it laminar or turbulent? So I got to find a Reynolds number. And then if it's laminar or turbulent, then I got to figure out if it's fully developed, right? So I have different equations for that. So I need to find the Reynolds number. I need to know if it's laminar or turbulent. And then I need to pick a correlation for my Nusselt number, right? Which will be based on that information. And to do all of these things, I need to know the properties of the fluid. So usually we would say, okay, we're going to determine the properties by looking at the average temperature between the inlet and the outlet of the pipe and look stuff up on tables. But step 2 here is pretty straightforward in this problem because we're told all the properties that we need. So that's good. I'm now done step 1 and I'm done step 2. So this should be step 3. So my box is in the wrong place, right? So now we're going to calculate the Reynolds number. So I just took an image of my picture of my sort of sketch up here and all the properties. And I know that the Reynolds number is going to be the velocity at infinity, right? So the velocity coming into the pipe, or the average velocity, times the diameter divided by the kinematic viscosity. I don't know the velocity coming into the pipe, but I do know the volumetric flow rate, and I can find the cross-sectional area, right? So if I divide the volumetric flow rate by the cross-sectional area of my pipe, then I can get a velocity, right? So that's what I've done here is I've taken the volume, or the volumetric flow rate, divided by the cross-sectional area, right? I worked that out separately in my calculator. I'm not sure about the rest of the problem, but I'd like to have an answer for the velocity just in case. So I see that that's 9.6 meters per second. I can calculate my Reynolds number, and it's 90,200 about. So that's bigger than 2,300, so I know that my flow here is turbulent. So now I know that it's turbulent, but I got to see, is it fully developed? So here, I know for turbulent flow, like we talked about in the multiple choice, that the entrance lengths for the hydrodynamic and thermal parts of the problem both happen at about 10 diameters into the pipe. So in this case, that's 0.1 meters, which means that it's fully developed for the vast majority of the pipe. So now I use the information that it's turbulent and fully developed to find the right correlation. So because it's turbulent, I know that I don't use these laminar correlations. We said this when we were doing this, but I'm going to try to never use this rough and transitional correlation. It's just a bit of a bear to work with, right? So I'm going to use the smooth pipe. So I guess maybe I should have written in my assumptions that this is a smooth pipe, or that would be a reasonable assumption to write down. But now I got to pick the value for n, right? The exponent on my Prandtl number. And in this case, because I have hot air moving through a cold pipe, my surface temperature is less than my fluid temperature. So Ts is less than Tm. So I know that the exponent here is not, the exponent here is not 0.4, it's 0.3. So now I have a Nusselt number correlation. And now with this Nusselt number correlation, I can solve for the heat transfer coefficient. So I use the Nusselt number correlation I have, along with the definition for the Nusselt number, h times the characteristic dimension divided by k of the fluid. First, I'm going to solve for my Nusselt number. So I know the Reynolds number. I calculated that already. The Prandtl number is given. So I see that my Nusselt number is 190. There's no units. And then I can rearrange the definition of the Nusselt number to isolate the heat transfer coefficient. I do a little bit of math in my calculator, and I find that the heat transfer coefficient is 33 watts per meter squared Kelvin. So that's good. I've answered part A. That's half the marks for the problem, right? So now I go to part B. What is the temperature of the air leaving the 15-meter long underground section of the tube? So this part's a little bit tricky because we have to remember how we find the temperature of the fluid that's moving in internal convection when we have a pipe with a constant surface temperature. So here, you can look on your equation sheet. So this is good why it's good to study with the equation sheet. And we can see we've got this equation for internal flow with constant surface temperatures. So this says the surface temperature minus the fluid temperature at whatever distance x that we're interested in, divided by the surface temperature minus the inlet fluid temperature, is equal to this expression that's spotlighted on the slide. Spotlighted just doesn't seem grammatically correct, right? So here, my x value is the length that I'm interested in, right? But in this case, that's the whole length of the pipe, right? So L is 15 meters. So my value for L is going to be 15. I put that into the exponential term. And then I work that out. Again, I mean, I've said this before, but I'm really good at punching things into my calculator wrong. So I'm going to just do this, right? Calculate the numerator first, then the denominator, and divide them both, right? The one thing, if it's me, if I'm going to mess up in this problem, one of the things that I really like to mess up on is forgetting that this exponential term is negative, right? The term in the argument here. So if you get a value here that's bigger than 1, it means that you forgot to put the negative value here, right? So please remember to do that, right? I guess you could get into a position in this case where maybe you could solve this. You could show that you could solve it symbolically, but maybe in part A, you didn't get the answer for the heat transfer coefficient. So I'm going to say that if you feel like this is the case in any of the problems on your exam here, and probably any of the exams you're going to write, do the symbolic solution. And then here, if you just couldn't find H in the previous part, you write down the symbolic solution and you just say, you make a note and you say like, I don't know what H is, right? Because I'm either not confident in my previous answer or maybe I didn't get a previous answer for part A. So I'm just going to assume that H is whatever, 100 or 50 or 1500. You just put a number in, right? And then you're still demonstrating that you knew how to do this second part of the problem, right? So here now we have a ratio, this dimensionless temperature difference here. We have a value for that. So now I can isolate my temperature at the end of the pipe, TL, right? So I moved this stuff around. So here I moved TML to the right, and I moved this term over to the left, right? It's a little sneaky. When I did that, I changed the delta T. See how the delta T here is TMI minus TS? And over here it was TS minus TMI. I could have just moved it over and multiplied that whole term by -1. It's the same thing. Right? So here as I'm working this out, now I can put values in. And I see that I get an exit temperature, an outlet temperature of 19.4 degrees. So that kind of makes sense, right? Because we were pulling, we pulled hot air in at something like 27 or 29 degrees, something, yeah, 29 degrees right on the slide, right? And we said that we're keeping the air temperature in the house at 23 degrees. So it makes sense that the cold air coming into the house is less than the average temperature in the house. So again, I don't know that this answer is right, but I feel pretty good about it. I'd feel worse about it if it was like, 50. So if the temperature was higher, then I'd feel like maybe I made a mistake with a sign somewhere. Or if the temperature was like -200 or something, because that just doesn't seem very physical. But I feel pretty good about this number. So now I'm going to move to part C. I see that part C is worth 5 points, but I'm still going to try to get those 5 points, right? So here it says, assuming the air enters the house at the same temperature found in part B. Again, if you didn't have a temperature, you just guess something. What is the cooling rate in watts provided by the air entering the house if the house is maintained at 23 degrees? And we have this hint that air leaves the house at 23 degrees and at the same rate as it enters the house. So I'm thinking about that, and I'm like, oh, we got this house, right? And there's air coming in, and there's air going out, and there must be heat coming in, right? And that's kind of the question, is how much heat is being removed from the house, right? So some heat is coming in, but because we're at steady state, we've maintained this temperature at 23 degrees. What's the heat load of our refrigeration system here? So again, when in doubt, use the first law. We're at steady state in this problem. We have no energy leaving the system except by mass. There's no energy generation in the house, right? And we're assuming that because the system is at steady state, right, we're not storing or depleting mass in the house of air, mass of air, so that the mass flow rate in is equal to the mass flow rate out. So then I can get an equation here that the energy that's coming in, the energy we're able to remove in this steady state situation, can be found. It's going to be equal to the mass flow rate of the air times the specific heat of the air times the temperature difference of the air, right? So here we're told that the air leaves the house at 23 degrees, but we found before that it entered the house just a little bit under 20 degrees. So we can see that we're removing 725 watts of heat from the house, sort of continuously. So that's the end of the first long answer problem. Does anyone have questions about either the method or the answers that we got? Okay, we will move on to the second long answer problem. Problem 2. The oil in a large industrial generator is to be cooled in a shell and tube heat exchanger with multiple tube passes and one shell pass using water as the cooling fluid. Water, at a particular specific heat, enters at 58 degrees Celsius and with a flow rate of 0.53 kilograms per second. Oil, which has a different specific heat, comes in at 1.2 kilograms per second at 75 degrees Celsius and flows through a thin-walled tube of 10 millimeter diameter. The internal and external convection coefficients are given. What is the total heat transfer rate for the exchanger if the oil exits at 71 degrees? What would be the required thin-walled tube length to cool the oil to 71 degrees, right? So heat exchanger design is one thing that we're interested in, something that's different than what we did in thermal. In part C, if one did not make the assumption that there was no heat loss to the surroundings, how would you answer, or how would your answer for required length change from what you calculated above? Provide a qualitative answer with an explanation. So qualitative means don't do math, right? Just sort of talk us through it. So again, I like to draw the problems out. So I know that on the cold side, I have water, or I have a fluid coming in, right? This is water at 58 degrees Celsius. I know the mass flow rate, and I know the specific heat. I don't know the cold outlet temperature. I know the hot inlet temperature. It's 75 degrees, and I know the mass flow rate, and I know CP. And I also know, even though it's not really given in the question part of the question, in the answers, it says, oh, what's the total heat transfer rate if the oil exits at 71 degrees, right? So here we're going to say that the oil exits at 71 degrees. So this is what my picture looks like, and I'm asked, what is the total heat transfer rate for the exchanger if the oil exits at 71 degrees? Right? And I'm told the internal and external heat transfer coefficients. Sorry about that. I had a bit of a brain freeze. Right? And I'm told the diameter of the tube as well. So here we're going to assume that the problem is at steady state, that the fluid and material properties are constant, that there's no losses to the surroundings, at least for the first two parts, and that the tube is thin-walled, so that there's no thermal resistance from the tube. I guess part of this is also that there's no fouling on the interior or exterior surfaces of the tube. So what's the total heat transfer rate? So whenever you want the total heat transfer in a heat exchanger, it's best, right, if we know the temperatures on at least one side of our heat exchanger. So here I know that m.Cp on the hot side times delta T is equal to m.Cp on the cold side times delta T, right? Because if I'm assuming that it's fully insulated on the outside, all the heat that's lost from the hot side goes into the cold side. So here we don't have all the information we need on, we don't have all the information we need on the cold side because we don't have the cold outlet temperature. We do have all the temperature, all the information we need on the hot side. So I can find this from the hot side. Also notice here that the delta T's are set up differently on the hot side and the cold side. So it's always the hotter temperature minus the colder temperature because I'm looking here for an absolute value. Right, so here I have an expression for the heat that's lost from the hot side of my heat exchanger. I know all of this information, so I can put it in my calculator. I got to check the units, right? And I get that this is 9,768 watts, right? Here, when I'm looking at the units, the kilograms canceled out. I get joules per second times Kelvin on the denominator, right? And the Kelvin, right? So this delta T in Celsius is the same as what the delta T in Kelvin would be. So that cancels out too. So I get joules per second, which is watts. So the problem doesn't ask me this. I've already finished part A. But again, so you wouldn't necessarily do this in a test. But because we know everything on the hot side, we can know everything on the cold side. So this problem easily could have asked me, what's the outlet temperature on the cold side? So then I would take this same equation, m.Cp times delta T, and it would be equal to Q, right? And we know Q from the hot side, and if they're the same, then I can get an expression for the outlet temperature on the cold side. I put some numbers into my calculator, and I find that that outlet temperature is 62.5 degrees Celsius, right? And that's nice, this 62.5, right? It's bigger than 58. So, and it's also less than 71. So it's kind of in the range where I know it needs to be, right? So that's good. I can't prove that it's wrong. Part B. What would be the required thin-walled tube length to cool the oil to 71 degrees? Right? So now I'm going to update my sketch because I know the cold outlet temperature here. But this part B is basically saying, you see, this is worth 35 of the 50 marks for this problem. Right? But it's saying do a heat exchanger analysis, right? So when I think about heat exchanger analyses, I think about this 2x2 matrix, right? So even if you don't draw this out, I wouldn't expect you to draw something like this out necessarily on your exam. But I like to think about it this way, right? So here our objective is we're sizing, right? And the method we're going to use, because this is a shell and tube heat exchanger with a tube bundle, right? It's not just a counterflow or parallel flow heat exchanger. So I'm going to use the effectiveness NTU process, and I'm going to use sort of this flowchart instead of this one. Although they're close enough, right? So hopefully, if you started doing the wrong sort of process here, you could easily see like, oh, I don't know NTU, so I must have to find effectiveness first. So we're going to pick the geometry. Our geometry is a shell and tube heat exchanger. It's got one shell pass, which means that there's no baffles here. So the fluid in the shell isn't forced to sort of snake back and forth over the tube bundle. It's got an even number of tube passes. We don't know how many tube passes there are. When we did the example in class, we were told there were 8 tube passes. Here it just tells us there's some even number. So we don't know how many there are, right? But I can look on my list and I see for shell and tube, right, with even passes, 2, 4, 6, 8, presumably, right? Then I use this equation, right? And so I need to find NTU and I need to find capital E, right? But to do that, I'm going to know the ratio of the big C's, so C sub R, and I'm going to know the effectiveness of the heat exchanger. But these are the expressions I'm going to use to get NTU. And from the definition of NTU, I'll get area. So now I need to find C min, C max, and CR. Right? So the hot side, m dot Cp, I know that number. Right? So 2,442 watts per Kelvin. On the cold side, I also know m dot and Cp. So I know this is 2183.6 watts per Kelvin. So I can get the ratio. Oh, so first I see that the higher number is on the hot side. So C max is on the hot side and C min is on the cold side. I can get the ratio of C min to C max. I always take the lower number over the bigger number, and that's just about 0.9. So now I'm going to find the effectiveness. So effectiveness is going to be the actual amount of heat divided by the maximum amount of heat. So I have two choices here because the actual amount of heat, like we said, can be big C on the cold side multiplied by delta T on the cold side. Or it can be big C on the hot side multiplied by delta T on the hot side. Now, what I like to do is I like to take whichever version of this is C min. So in this case, C cold is C min, right? So I would use this equation and cross out my big C's. And then I would just get a ratio of, I get a dimensionless temperature difference. But I can only do this because I took the extra time to find the outlet temperature of the cold side. So if you didn't do that, there's nothing wrong with using this equation. It's just your big C values won't cancel out. So there's more stuff to punch into your calculator. And as I've said multiple times, I'm really good at making mistakes when I punch stuff into my calculator. So there's nothing wrong with, both ways I'm punching more things into my calculator, right? Because this way it doesn't look like it now, but I had to find TC out, right? Which involved doing some manipulation. And over here, I would have to just put more stuff in. So it's 6 of one, half dozen of the other, I guess. And the problem never asked me to find TC out, so I didn't have to find it. So now I know the effectiveness. With the effectiveness, I can calculate NTU, right? Because effectiveness is a function here. So we can see NTU is a function of big E and CR, but big E is a function of effectiveness in CR. So if I know CR in the effectiveness, then I can find my NTU. So first, I need to find big E. So this is 2 over the effect. Well, I'm not going to read the math to you, right? But I know all these values because I know the effectiveness and I know C sub R. So I put this into my calculator and I get that big E is equal to 4.2. I put that into my expression here for NTU, right? And I get that NTU is equal to 0.36. right? If I did this wrong, again, so if I did this and if I forgot this negative sign, like your NTU can't be negative, right? So if you get a negative value here, it means you did something wrong. So now we're going to use NTU to find the area, right? So NTU is going to be the effective heat transfer coefficient times the area divided by C min. So I can rearrange this expression to find the area. But here I don't yet know the effective heat transfer coefficient. So if this problem was really long, it might ask me to find H of the internal flow through the tubes, right? But here we didn't do that. It told us H hot and H cold. So we're going to assume that the wall of the tube is small, so it doesn't add any extra thermal resistance. Or another way to think about that is it doesn't contribute to this effective heat transfer coefficient. So here we put our values in. These are both the same units, so I didn't include the units, right? And I get 1,920 watts per meter squared Kelvin. So now I know capital U, so I can find area by using this expression. I put some numbers into my calculator, and I find that I need 0.41 meters squared worth of area. It's not what the problem asked me for. I think if I was grading this problem and you forgot to find the length of the tube and you just left it at the area, you sort of would have demonstrated that you already knew the heat transfer part, right? But it does ask us for the length. So here, I guess it is important to know that the area that we're talking about is sort of the wetted area inside the pipe. So it is important to know that this area, it's not the cross-sectional area of the pipe, it's the perimeter, which is pi times d, multiplied by the length. So it's the area of the pipe that's touching the two fluids. So here we can get an expression now. We can isolate for the length of the tube. This is the total length of the tube, the area divided by this perimeter, right? And we get that this is 12.9 meters. So it's got to be a pretty long tube, which is why it snakes back and forth across our heat exchanger. An even number of times, they told us, but we don't know how many. So now part C, this is worth 5 points. If one did not make the assumption that there was no heat loss to the surroundings, how would your answer for required length change from what you calculated above? And provide a qualitative explanation. It's too bad. If we were in class, I would ask for like a show of hands. How many people think that the length would need to be longer, and how many people would think that the length would need to be shorter? So kind of think about what your answer would be, right? But here's what I wrote. If heat was being lost to the environment, some of the heat from the hot side would go to the cold side, and some of it would go into the environment. So there'd be less, this is not what I wrote, right? But the cold side would have to take in less of the heat, right? So this would increase the amount of heat transferred from the same heat transfer area, right? Because there'd be some extra bit lost. So we would expect T hot in, that should be T hot out, to be lower than the value calculated in the model. In that case, we would expect to be able to reduce the length of the tube if we were losing heat to the atmosphere. So basically, because we have a second heat sink, we would expect more heat transfer, and so we'd need less heat transfer area. So if we knew the resistance of that heat loss, so if you were told like a heat transfer coefficient on the outside of the heat exchanger, or maybe like an insulation thickness or something, you could find a net resistance to the outside world, especially if you knew you'd probably have to make some kind of assumption or take a measurement of what the temperature on the outside of that heat exchanger was. Then you could find out how much heat you were losing to the environment. And then you could say, that would go back into your first law part of the problem. And then you'd find out how much of the heat was lost to the environment. And that would let you know how much heat goes into the cold side. So then you'd get a different value for temperature of the cold on the outlet. And that, I believe, is the end of the practice exam, which is technically the end of the course. Does anybody have any questions about the long answer problems?
Is there going to be any sort of other equation sheet besides the one that's on my courses? Like a couple of the equations that you had to use in those questions don't seem to be on there.
No, so you will not get another equation sheet. You will potentially get an equation, or not an equation sheet, but if you need like, so you would get an equation sheet like for if we need like this. You're not expected to memorize these equations. Is that what you mean?
Yeah.
So if you need these expressions, if on the exam you need the expressions for effectiveness as a function of NTU and CR, like these would be provided. So basically, big complicated equations like this that are not on the sheet, we'll give you. We'd give you a choice, so we would probably print this whole table out, and maybe also the table with effectiveness, like so the other way around. But sometimes this has come up where people were asking, like, do I need to know? I can't think of a good example right now, but I think so complicated things like this that you wouldn't be expected to memorize, I think we will provide. But some things I think you're expected to know. Like I don't know if it's on the equation sheet, but if you like how do you add together resistors in parallel and in series? I don't know if that's on the sheet, but if it's not, then that would be something that we wouldn't give you a separate equation sheet for.
Okay, thank you.
You're welcome. Other questions about heat? I guess are there other questions about? So I guess we just came out of a faculty meeting where some professors were talking about how students in their classes had expressed some concern over maybe what's happening in the fall. And I know I've referenced a couple times that we won't know if we'll be sort of virtual or in person in the fall, or maybe some kind of a mixture of the two. But I do want everybody to know that we will be delivering material. So, I mean, we will definitely have classes in the fall. I don't know if there's other, I remember when we were on spring break, we had some meetings in this time where people just had sort of general questions about what was going on. I don't know if anybody has other questions in that vein.
Do you know how the senior design classes have been going this semester in the case that the fall were to go virtual as well? I know I'm definitely concerned about how senior design is impacted.
Yeah, I think that's a very good question. Senior design is a bit of a funny class because it's not exactly in our department because it's kind of shared throughout the college. So I haven't been present in any meetings where people were talking specifically about senior design. It's certainly a good question. And I think in some ways it would be similar to lab classes also have this problem of, you're actually supposed to be doing some practical things, and it's a lot easier to give a lecture online than it is to design and build something. I will filter that question up and try to answer it basically through email with the response that I get, because it's a really good question, but not one that I know the answer to.
All right, thank you.
Sorry, I wish I had more answer, which is sort of I guess I asked for questions, right? But it's, some of them are just, I don't know the answer, but maybe that's comforting too, to know you're not the only one that doesn't know. Another thing that came up in faculty meeting was access to counseling services. So RIT is still providing counseling services. So if you feel like you're in need of those kind of services, I think through their same channels, I'll get an email out too with links to those services as well. I think there is some added complication if you're no longer in the state of New York, because counselors, the way counseling works is they get certified to practice in state by state. So if you're no longer in the state of New York, what we learned in faculty meeting on Wednesday was that, they can still contact you, they can still talk to you, but they would be more trying to set up, who you can talk to in the state that you're residing in. So it's based on the state that you're actually physically in right now. So even if you're, even if you list your permanent residence as being in Rochester or being in New York, if you're currently in California, say, then they can still sort of help you access different things, but they can't provide actual counseling. But they should be able to help you find resources where you are. That's true for most of the counselors. I think the other thing that we found out was that some of the counselors are certified in multiple states. So again, there may be solutions if you're looking for that. And I'll put together an email and or maybe an announcement on the site, or maybe both, just so that access, so you know where to access those services if you feel the need, because I know it can be stressful. So are there any other questions?
Have they said anything?
Morning?
They're going to decide about classes in the fall?
I have not heard anything about when a decision would be made. I think there's sort of at least two levels to that. So first, the state government would have to, right? So as of now, at least as current as my information is, I think in the state of New York, we're locked down or, social distancing or sheltering in place till at least May 15th, I believe. I did see on the news the other day that that they've appointed, I think maybe the assistant or associate governor or something, plus someone from the Rochester area is looking at how to bring things back in the Finger Lakes region, which presumably we're part of. So I'm sure that there's some kind of a tiered way of bringing things back. I don't know exactly what that is. But so first we would need approval from the state, and then I would imagine RIT would have some process of its own. But I think we don't know any kind of timelines for that. But it's certainly, I wish I knew the answer, right? Because, yeah, it'd be good to know. I think there was another question at the same time as yours.
Yeah, this morning there was a email sent out as like an update of the pass-fail option.
Okay.
And honestly, up till this point, I've been pretty unclear on when pass-fail can be declared.
So my understanding of the pass-fail, I don't know if I got that email, or at least if I did, I didn't see it. So my understanding of the pass-fail option is that professors input the grades as they normally would. So I will input a grade into SIS that's a normal letter plus or minus type grade. My understanding is that students will see what those grades are. And then students can make a reversible decision about whether or not they want it to be pass-fail. So if when you see the grade, you think, well, I would like to convert that from, a B plus to a pass or whatever. It's not really pass-fail, right? There's pass, satisfactory, and right? There's 3 tiers, right? So you can basically, so there's an answer here that's much less long-winded than mine. So you can make your decision after you see your letter grade, and you can reverse that decision any point up until your degree is certified. And it says here, if you're graduating this semester, it's before May 15th. So I would imagine we may have some people in the class that are graduating this semester. Any other questions?
What do you think it would look like if we were to do some sort of combined, partly online and partly in person?
Yeah, I think that's a good question. I haven't heard anything approaching concrete. I know that there's a committee at RIT that's looking at this, and our department head is on that committee. So it's nice that at least we have a voice from the mechanical engineering world. I know that it has been discussed that potentially freshmen would be on campus, but other people wouldn't be. I know at the graduate level where people are, I don't know. I guess there's optimism that at the undergraduate level, people will be able to come back. It's a little difficult in the graduate level because we have so many, right? It's like I said, optimism doesn't mean that we know, right? At the graduate level, I know there's a lot of international students, so people would need visas to come. And I think that's, so we could definitely have a case at the graduate or the undergraduate level where maybe a small subset or maybe part of the class is meeting like we normally would in a classroom, but then another part of the class is interacting with things virtually. So, for example, the videos that I posted online, people could look at those, or maybe we're even streaming stuff real time from the classroom that people can watch if they elect to be at home. But I have heard no concrete plans. I think right now, because we don't know, I think RIT is trying to look at a whole wide range of potential solutions. Any other questions? Well, I have really enjoyed the class. I hope that, I hope that it hasn't been too bad over the last, whatever it's been, month and a bit. I appreciate people being here. One of the things that I've really been impressed with is how many people have been coming to these when we decided to do these virtual lectures. I think one of the things that we weren't sure about was how many people would be here. So it is, I do really take heart in the fact that you're here and that people are here, despite, the circumstances that we're all in. So thank you very much. It's been a pleasure. And like I said, I will be available in my office hours and also in our class time on reading day. If you have questions that you'd like to ask me in that time, please send me an email with a time that works for you in that time, and I will be in the room. All right. Well, thank you very much, everyone. Appreciate it.